Hello and welcome to today's lecture on transformer math and introduction to LLM inference. In today's lecture, which is divided into two parts, first we'll discuss transformer flops accounting. So we'll look at the individual operations going on in a transformer layer and say how many flops are being consumed by that and how many number of parameters are associated with each operation. We'll do it for training, which means that we'll consider both the forward and the backward pass. In the second part of the lecture, we'll take a deeper look into LLM inference. We'll see how the autoregressive nature of the LLM enables us to use what's called KV cache to speed up the inference process. This cache divides the inference into two stages called the prefill stage and the decode stage. It's a decode stage which is harder to get to make more efficient on the GPU. And for the decode stage, we are going to see how we can change its throughput latency by varying the pass size. We'll do some back of the envelope calculations for Gemma 2 9 billion parameter model on an H100 GPU. And we're going to derive the throughput latency numbers with respect to the pass size for this model. Let's get started with the first part of our lecture. So first let's look how many flops are involved in some common matrix operations. So if we are doing a dot product of two vectors of size p each, so in effect we are doing p multiplications and p additions. We consider p additions because normally we would accumulate the sum in a register which would be initialized to 0. So first we'll add this, then whatever comes after this. So in effect we're adding p numbers to the register, so p additions. And this gives us 2p floating point operations for the dot product. If we were doing matrix vector product where A matrix A is of shape n by p and the vector x is of shape p, it can be written, the A matrix can be written in this way, and here's the x vector. The resultant output is an n-dimensional vector where each element is dot product of a particular row of A with x. So in effect we are doing n dot products, and each dot product involves vectors of size p elements, and we saw here each dot product takes up 2p flops. So overall this takes up 2 np flops. Moving on to matrix multiplication. So A is of shape n by p, B is of shape p by m, the output vector C is of shape n by m. Each element of the output matrix Cij is basically a dot product of the ith row of E matrix and the jth column of B matrix. And each of these vectors has p elements, so they are p element long. So computing Cij needs 2p flops, and we are calculating n times m such elements. So overall we have 2p mn flops for the matrix product. Consider a linear layer in an MLP. So here we first of all start with x as the input. In the very first layer we multiply it with w1, get the intermediate activation z1, and then do a non-linearity followed by the next layer. So the next layer has a linear projection with W2 followed by a non-linearity, and this goes on. Let's focus on this linear layer, this part here, and we want to say how many flops are needed in the forward and backward passes just for this linear layer. So for ease of notation, let me denote A1 here by capital A, W2 by capital B, and Z2 by capital C. And let's assume that A is of shape n by p, B is of shape p by n, and C is of shape n by m, just like in the previous slide. So to get Z2 here, doing in the forward pass here, I multiply these two matrices to get Z2, and that can be written as obtaining C from A and B. And we saw in the previous slide that this operation takes 2p mn flops. So the forward pass of just this particular portion of the network, it takes 2p mn flops. In the backward pass, we have the upstream gradient with respect to the output of this linear layer, which is C. So we have del L by del C, derivative of loss with respect to C, and we are interested in obtaining the gradient of the weights. So B here stands for weights, and the gradient of the activations. And we need the gradient of the activations because we need to pass on this for the backward pass for the layers which come before this in the network. So in effect, we need to calculate partial derivative of the loss function with respect to A and partial derivative of L with respect to B. So del L by del A, by chain rule, it is del L by del C times del C by del A, and matching the dimensions, it can be written in this way, del L by del C times B transpose. Del L by del C is the same shape as C because L is a scalar, so it's n by m. B transpose is m by p, and so we are multiplying two matrices here, and this takes up 2 PMN flops. And similarly for the weight gradients, it's E transpose times del L by del C, and E transpose being P by N, and del L by del C being N by M. This takes up 2 MN flops. So the calculation is exactly similar to what we saw in a couple of slides ago for matrix multiplication. So in the backward pass for this linear layer, we would be doing 2 PMN flops here and 2 PMN flops here. So this is 4 PMN flops in total, and this is twice the number of flops which we did in the forward pass. And this is generally true that we end up doing more flops in the backward pass as compared to the forward pass. So up to this point, we have been considering matrices of dimension 2. For tensors which have dimension greater than 2, the product is ambiguous, so we have to specify it more clearly in some way. As an example, consider batch matrix multiplication. So consider multiplying these two tensors of shape these, where B can be thought of as the batch dimension, and the output which we'll get, that let's say it has the shape P N M. The tensor product can be specified in this way. So each element of the output matrix, here indicated by these indices small b, small n, small m, the B N M index of the output matrix is given by this relation. So we take the Bn k of x, bkm of y, and sum it up over all the k indices. And this, it takes up to be the whole thing to obtain z, it takes up to be nmk flops. And this is because for this computation here, if you expand it, we are doing k multiplies and k adds, so that makes it 2k flops to obtain one output element, and in total we are obtaining p and m output elements, so that makes it in total 2 b and m k flops for getting the output. Now the terminology which is used is when we sum up over an index, that is called the contracting dimension. So here k is this dimension here is the contracting dimensions. So the contracting dimensions are the ones which are summed up over. Batching dimension is the one which is present in all the tensors, but we don't sum over them. So we are not summing up here over the B dimension, although they are present in both the tensors. And those dimensions which are present only in one of the two input tensors and also in the output tensor, those are called the free dimensions. So here, N and M are the free dimensions. So one thing to note is that the contracting dimension here, usually to make this whole operation fast, to make the reading of these values from memory faster, it's better if these tensors are laid out in memory in such a way that K is the fastest varying. So whichever index is the contracting dimension, that should be the fastest varying in memory. So for instance, here, after one element of tensor Y, the next element of this tensor should differ from this dimension by 1. So, yeah. So when this is the case, then memory read, it becomes more efficient. Another thing to note is that for the batching dimension, one can consider these operations to happen in parallel for the batching dimension. So one can parallelize this one with respect to B. So maybe there's one thread which does this computation for a particular value of B. There's a convenient way to specify a tensor product, which we wrote here in this relation by what's called an INSUM string. And in this string, in effect, we specify what is the contracting dimension, what is the batching dimension, and what is the free dimension. And in a way, we specify this product. So the INSUM string for this tensor product would look like the output dimension B and M is obtained from these dimensions of the input B and K, BKM. So we see that B is present in both the inputs and also in the output. So B is the batching dimension. K is present in both the input tensors, but not in the output one, so it's a contracting dimension. And N and M are the free dimensions. Let's look at the self-attention module within a transformer layer and see the kind of operations going on. So here X is the input coming into that self-attention module, and these are the operations going on. So here I have not shown the MLP, will come to it in a little while. The notation which we are going to use is, say, by B we mean the pass size, and by S we mean the sequence length. Basically in each sample, so let's focus on training here. In each sample, how many tokens are there? D is what's called D underscore model or the embedding dimension. H is the attention head dimension, and N is the number of attention heads. So here in most transformer models, we have what's called multi-head attention, and that enables the tokens to attend to each other in different representation subspaces, and thereby, because tokens can have many different kind of relationships, so having multiple attention heads, it enables them to form these different kind of relationships among themselves. Usually, we take H as D by N, so we divide the attention head dimension, so we divide the embedding dimension by N to obtain H, and this is in a way to ensure that when we have multiple attention heads, we keep the amount of computation same as the single attention head. So for simplification, let's consider the batch as having just one sample. So X is S, so it's the sequence length, and each sequences has an embedding of dimension t. So in effect here b is 1 and we have only s and t. And a transformer block can be thought of as taking in an input of some shape, in this case s by d, and it emits the tensor of the same shape s by d. So the dimensionality, the shape of the tensors are always preserved in the transformer blocks, and that's why we can just stack them one on top of the other. This also holds for the self-attention module. So the output of the self-attention module is also of shape S by D here. Let's look at the linear projections, the key query value projections happening in the attention module. So we take in xi, which is the embedding of one token. Remember that I'm considering the batch only to have a single sample here. So xi is a d-dimensional vector, and then multiplying it with wq, which is d by h, I convert that, I project that d-dimensional vector to h-dimensional vector to obtain a query vector for that particular token. And similarly I do to obtain the key vector and the value vector. So one thing to note is these operations, when they correspond to these here, in general, x can be of shape BSD, and then the weight matrix for query, it can be of shape D and H. So here I showed you D by H, but there can be more than one attention head. Here I am considering only a single attention head for simplicity. And then multiplying this, we get the output tensor of this shape. So consider n equal to 1 and b equal to 1. Then just as we saw here, the output, each token in the sequence is projected into an h-dimensional vector. And same thing for key and value. And this operation here, in effect, what we did was we did contraction over D in all of these cases. So D is the contracting dimension here. Now, one more thing that can be observed is that these projections of the sequence of the token embeddings, they happen for each token in the sequence individually in parallel. So this multiplication, it can be parallelized over B and S. And that's a good thing. So that's one good thing about the transform model, is because the training can be parallelized to such a high extent. Then we think about the dot product attention by multiplying the query vector and the key vector, and again limiting ourselves to single attention head. So consider the query vector of a particular token qxi. I obtain its dot product with all the other tokens in the sequence kxj for all j's going from 1 to s. And then once I have these s values, I do a softmax on these s values. So that's what I've indicated by j here. So for a particular query token, I get its score with respect to all the other tokens by doing this dot product. I scale the scores for numerical efficiency by under root of h, and then I do a softmax over those s values to give me the attention of the ith token with respect to the jth token. And in language modeling, we typically apply a causal mask on these outputs. So basically, one token can only attend to the tokens which are before it in the sequence. And for the others, so for j which are greater than I, this dot product is set down to 0. But we have not shown that here. One thing to note here is that although it looks like S the S dimension in the query matrix is different from the S dimension in the key matrix. Here, S is the token sequence in the query matrix, and here it's the token sequence in the key matrix, and those are different things. So S is neither a batching dimension nor a contracting dimension. It's the free dimension. And a better way to represent this is by this INSUM strings. So the output BS, it should be S dash in like for more clarity, N, because S and S dash, they represent different things, is coming from BSNH and BSS dash NH. So that's one small thing. And once having obtained the attention weights, we can do a weighted average of the value vectors. So for the ith token, I do a weighted average over all the S tokens multiplied by the attention weights. The output of this is H dimensional, and we convert it to D-dimensional vector by multiplying it with the output weight matrix. So the output weight matrix is H by D dimension. And this is also done because, as we said, that the input and the output of the transformer block and even the self-attention block is, the self-attention module is, it has the same shape as the input. They have the same shape. After the self-attention module, we have the position-wise feed-forward network, which we can represent it in this way. So it's basically a linear layer followed by a non-linearity followed by another linear layer. So we take in, so here X is of shape BSD, and consider B equal to 1. Xi is a D-dimensional vector for a particular token in the sequence. And the operation which is happening, so the MLP operation is happening for each token in the sequence individually, independently. That can be represented in this way. So linear layer followed by non-linearity followed by another linear layer. And the resulting output is again D-dimensional. So after we multiply with Wn, the D-dimensional embedding of each token, it gets projected onto an F-dimensional embedding. And usually F is larger than D, almost like 4D. And then it is down projected back by W out to, again, a D-dimensional vector. So overall, the one transformer layer would look something like this. The attention layer followed by the MLP, taken both together. We did talk about, we are going to shortly talk about layer norm and the residual connections. So in the MLP layer, for the first linear projection, we multiply these two tensors, and so the number of training flops we have for this is, just like we saw earlier, it is 6 BSDF, so 6 because 2 BSDF from the forward pass and 4 BSDF from the backward pass. And to see to make it easier to obtain this, you can just multiply the shapes of all the tensors, multiply all the dimensions of the two tensors, ensuring that you don't multiply anything twice. You don't multiply the contracting dimension or the batching dimension twice. So everything just multiplied once. And associated with this, like the number of parameters in Wn is D times F. The relative nonlinearity, it is acts per element, and here it's about BSF flops, the same as the tensor on which it is acting, the number of elements there. It doesn't have any parameters associated with it. And the output linear layer, it again is 6 BSFD flops, and the number of parameters is DF. So we can ignore the number of flops in nonlinearity because the other two quantities, they have a multiplicative factor of D, and D is usually quite large for typical LLMs, like in the order of a few thousands. So this quantity is much smaller than the other ones. And so in the MLP layer, in one transformer layer, the MLP takes up 12 BS DF flops, and the number of parameters is 2DF. Often we take the hidden dimension of the MLP as 4 times the input dimension, 4D. So the number of parameters becomes 8D square. For the linear projections going on in the self-attention module, so we obtain the query key and value vectors for each token in the batch, and for the output of each attention head for every token, we back project it to a d-dimensional vector. So for these tensor products, just following the calculation which we had done earlier, these are the number of training flops which we have associated with these linear projections. And these add up to be 24 BS DNH. For each of them, we have DNH parameters, basically the number of parameters in these weight matrices. And in total, per layer, we have 4 DNH parameters associated with the self-attention module for the linear projections. Usually, as I said before, to keep the computation sort of limited, we take NH is equals to D here usually. So the number of parameters is 4D square for the self-attention module. And we'll see like the dot product attention in the self-attention module, it doesn't involve any parameters. So effectively we can say that the MLP takes up twice the number of parameters as in the self-attention module. So this is a useful thing to remember, that it's the MLP which often dominates the parameter count. Looking at, for a particular layer, looking at the dot product attention, so as we said that the number of parameters we'll see when multiplying the Q query and the key matrices, these are basically like sort of intermediate activations and they don't involve any parameters. Multiplying them, it involves 6BS SNH number of flops. So recount again, like how the S here and S here, they have different meanings and they are not the batching dimension. So the output of this we are denoting by capital L, and it's of this shape BSSN. And for this, when we do softmax, basically we consider one particular token in this dimension, and then we apply softmax over all the tokens in this dimension. And for this one, the number of training flops is actually a small constant times the number of elements in this tensor. One way to think of it is that in the forward pass, we take every element, we do an exponent, we sum them up, and then we divide them. So we are doing a small number of operations for every element in the tensor. So it's K, B, S, S, N, where K is a small quantity. And then we take these attention weights and multiply it with the value vectors to obtain this quantity, 6B, SS, NH, to do these many training flops. So this quantity here, the number of flops for softmax, it is smaller by the other flops by a factor of H, and H is usually in at least a few hundreds in model transformers. So this can be ignored. And adding up the other two training flops, we have 12 BSS NH number of training flops with 0 parameters. So we see that the number of flops to be done in the dot product attention, it scales quadratically with the sequence length. So there's also layer norm involved in every transformer layer, and even for this, we actually do only a small constant times, a small constant number of operations per every element in the tensor. So recall that for every d-dimensional vector, we compute a mean and a standard deviation, and then multiply them with the scaling and the shifting parameters. So the number of parameters involved are, for every layer, it is 2D. So there's a d-dimensional parameter for the scaling parameter gamma and d-dimensional for the shifting parameter beta. And finally, at the end of the layer, of all the transformer layers, there's the unembedding matrix, which takes a d-dimensional vector and converts it to a vector of size, the vocabulary size. And this just happens once at the very end. And this is just like matrix product. So the number of training flops is very much like the linear projections which we saw earlier. But the number of parameters is each element in the embedding matrix is like a parameter. For the embedding matrix, again this happens once at the start of the transformer, and in the forward pass, basically we don't do any flops because it just involves some memory lookup. And in the backward pass, also we do a small number of flops with what is called the scatter add operation. Overall, the number of flops being done, the training flops, is very small, so we can ignore for the flops for embedding. And it has the same number of parameters as the embedding matrix. So all of these, the layer norm is, as compared to other quantities which the number of flops we saw earlier in the transformer module, it's much smaller than them. In the other ones, you typically had BSDNH or BSDF. So we are missing those factors, and those are actually quite large. So we can ignore this within a transformer layer. For the unembedding matrix, this quantity is actually quite significant because D and V can be quite large. So we do consider this, but we ignore the embedding flops. Assuming training with short context length samples, in that case, we can ignore the dot product, attention, training flops, just as for rough calculation, and consider the flops going on in the position-wise feed-forward network and the linear projections in the attention module. So the total number of parameters for all the layers of the transformer is 2df coming from the MLP in each layer, 4dnh coming from the linear projection matrices in the attention module for each layer multiplied by the number of layers. So the number of tokens in a batch, we can write it as B times S. So we have a batch of samples, each batch is S tokens long. And adding up the training flops for the MLP layer and the linear projection of attention layers, for all the layers, we have this quantity. So basically, we added up this 12 BSDF for MLP and 24 BSDNH for linear projections in attention. And then we multiplied it with L for all the layers. And this can be written as 6BS times this quantity. And looking here, we can rewrite it as 6 times the number of training tokens times the number of parameters in the network. So this is a useful thumb rule to estimate that how many flops are we going to need for one epoch of training as we vary our training set, and as we change our model, maybe make it bigger and smaller, make it bigger. So this is a useful thumb rule, and then one can estimate how much time it might take to run on whatever GPUs one has. The unembedding layer also follows this kind of rule. So there we saw that the number of training flops is 6 BSDV, where DV is the number of parameters and BS is the number of training tokens. Okay, so this calculation is useful not just to estimate the number of training flop, but also we will see that the calculations really carry on very nicely to the even the inference phase, and it will help us look at inference and see like how much of time are we spending on different computation and which are the bottlenecks for us. What about the dot product attention, which we ignored in our calculation? So with respect to the linear projection flops, both in MLP and in attention, so this is the dot product attention flops, and these are the linear projection flops. So the ratio of this one, we can rewrite it assuming f equal to 4d and d equal to nh, which are commonly used in most transformer models. So we can rewrite this ratio as s by 6d. And when the sequence length during training becomes greater than 6 times the embedding dimension of the model, the dot product attention starts dominating the matrix multiplication flops. And our previous calculation, our approximation is no longer very valid. So let's take like some common open source models, looking at Llama 2 70 billion parameter model, whose D is of this size. The sequence length, at the sequence length of 50k tokens, our dot product attention will take more flops as compared to our matrix multiplication, which is quite a large quantity, which is quite a large value. And for Gemma 27b, we have, after 24,000 tokens, the dot product attention starts dominating. So as models become larger, the D dimension is usually becomes bigger. And as D becomes bigger, that's an indication that we are doing quite a lot of computation in position-wise feed-forward network. And the sequence length at which the dot product attention has to start dominating that also becomes larger. But thinking about long context training, which we are oftentimes interested in, then this quantity becomes a concern because we see that this scales as order S square. And to enable long context training, we try to make the dot product attention go faster by techniques like flash attention, which we'll see in later lectures. Thank you.